All right. Hello, everyone. Welcome to Machine Learning Introduction for Life Sciences students. My name is Nikhil, and I'm joined by Jerome. And today we're going to talk about some of the topics in machine learning, as if we are on a panel discussion or a conversation. We thought this would be a more interesting way of presenting our material, as there are many other YouTube videos online that you can look. So we are trying to discuss some of the topics that we found confusing when we were learning about these things together. And hopefully that will provide you a more interesting conversation on machine learning. So let's start with the basic questions. What is machine learning? Technically, machine learning is just a computer algorithm that improves automatically by looking at new data that we basically provide to the algorithms. And through the data, they will learn interesting relationships between an input and output. So specifically in life sciences, this is extremely useful because if you think of the fields like biology, medicine, or even environmental sciences, all of these fields have an extremely complex phenomenon that we're trying to understand and make some predictions about them. And so they have a bunch of variables, usually more than a handful of variables. So it gets difficult to understand the relationships without having large amount of data. And so machine learning definitely helps us to model these complex relationships within this large set of variables when we have a large amount of data. But we'll talk about this point again and again. But the goal of machine learning models is usually provide accurate predictions and not technically the explanations for these phenomena. And we'll talk about this more in later slides as well. And so when do you use machine learning? It's basically when you have a prediction task, that would be a supervised learning. And otherwise, you can use it to understand your data in a low dimensions. So if you have very high dimensional data, you can use unsupervised learning algorithms to find a low dimensional representation of the same data to make it more manageable for yourself. And the figure on the right basically talks about where does machine learning fit into all the buzzwords that we have today. So machine learning essentially is a subset of artificial intelligence. Artificial intelligence itself is a huge field. And the neural nets or the deep learning, which are more buzzwordy these days, are a subset of machine learning themselves. So machine learning models have very different flavors and types, and neural nets is just one out of them, one class of models out of them. And yeah, so before we move on, I was going to ask Jerome, what type of models does he use and what type of projects he has used so far machine learning for?
So examples of projects for which I've used machine learning. One was meta-analysis of neuroimaging publications. So based on the text that is in an article, we tried to predict where in the brain they would report observations or activations. And we used linear models for this based on the frequencies, the occurrence frequencies of terms in the text. And another one is predicting some diseases in participants in the UK Biobank, which is a huge data set of UK residents. So based on some measurements such as their alimentation, some blood samples and so on, try to predict if they have a disease or not. And in that case, since the dataset is much larger, we were using nonlinear models, gradient boosting.
So most of these models are supervised learning models, is that correct?
Yes, both of these are supervised learning models, cool. Which is what we'll be talking about today, I guess.
Yeah, so yeah, we'll talk about that in the next slide. Yeah, so same for me, I think most of the models I have used are supervised learning models. One of the common problems I have dealt with is segmentation, where we get a medical image and we have to basically identify different organs or different structures in the brain, pixel by pixel. So it's a classification model that we use on medical images. That's one of the common things I have done so far. Okay, so moving on. So we should go through some basic terminology because it can be really confusing. So what you're seeing on the left is the input or the number of samples. So all the rows represent different samples that you're collecting. So in terms of the project we just talked about, it could be a different individual that's basically represented by each row. And the red bar would be, it's a clinical outcome, maybe a symptom or a classification for diagnosis. And the columns themselves represent features. So these are essentially, for if you have an image, there would be the pixels or the voxels of an image, and they're usually arranged in different columns. There could be also demographic variables like age, sex, some genotype type of things. And the goal is to use this information on your left, which is usually represented by X, and map it onto a Y. That's your outcome. And this is where machine learning models come into picture. It's basically trying to learn a function that basically takes your input X and provides an outcome, that's the Y. And just to reiterate the terminology, again, the number of observations are also called samples, which would be, for example, the individuals, and the features are different types of information on that sample. In images, that would be different pixels or different voxels that you're collecting in an image. Anything else have I missed, Jerome, in terms of the confusing nature of these terms?
No, I think you've covered everything. Just we'll add that features sometimes are given different names. So some people might also call them regressors, descriptors,
predictors as well. Yeah.
Predictors, yeah, or independent variables. And Y is also sometimes called the output, the target variable, the outcome, or the dependent variable.
Right. Yeah, no, that's definitely was confusing for me as well. And in practice, would you say the types of data sets we deal with, especially in life sciences, would have more features than number of samples?
It really depends, but at least when we're dealing with three-dimensional images, there is one feature, as you said, for every voxel in the image. So very often these, so P here is the number of voxels in the image, and it becomes huge. So in this situation, we often have P that is much larger than N.
Right. Yeah, I think in my experience, that's true for some gene expression data as well. There are like a huge number of variables that you can collect from these biological assays. And number of samples always seems to be a problem when we're having few number of samples is always a problem when you have large amount of features. So yeah, moving on, there are different ways you can basically classify different machine learning algorithms. The one easy way that I have found over the years to think of them in this 2x2 rubric. So where these columns are basically types of models that do either supervised learning or unsupervised learning. In the supervised learning, you basically have a label. So for example, you have a clinical diagnosis or score or the value for the pixel, which structure it belongs to type of things. So you have classes or labels handy. So you're trying to help model learn the relationship between the input and the output using this labeled data for supervised learning. Whereas for unsupervised learning, you don't have access to outcomes or output labels, but you're trying to basically understand some underlying representation of these data sets. And usually you can do that by some sort of dimensionality reduction technique, like PCA that Jerome will talk about later, or we can also do clustering, which is a very common thing people do all the time. And the rows here basically represent if your outcome is continuous or categorical. So if your outcome is continuous in supervised learning, you'll be doing regression, which is very common technique, linear regressions. Or if it's classification, then you do something like logistic regression, and you'll get a categorical or a binary output. So it's just a useful way of dividing your machine learning algorithms based on the type of approaches they use. So again, moving on, like I said, we're only going to focus on supervised learning in this particular module, and we'll talk about unsupervised learning in the next module. And the goal of supervised learning is to learn parameters or in some cases, or most cases, the weights of the model that map X onto the Y. So there are different types of models that you can use. And the most commonly used are the linear or logistic regression models, which are very simple models to kind of visualize and see. But there are also highly popular SVMs or support vector machines, which try to maximize the margin between the two classes that you have. And also a lot of commonly used tree ensemble methods, random forest, gradient boosting. These are, again, decision trees, just many of those put together to make the predictions. And lastly, the most popular one these days is the artificial neural networks, which I said earlier is a subset of machine learning models. And artificial neural networks also come in a huge amount of different architectures, and they have been extremely successful in certain tasks these days. So we're not going to go through all of them together or all of them in detail, but we'll talk about linear regression and some common practices that you should be using while validating these models or using these models. And they should apply, those rules or those strategies should apply to all the models of your choice. So this is an example of how do you basically learn model parameters or model weights for linear regression. So on the left, I'm basically showing how the linear regression model is defined, where you have an outcome variable y, and you have x1 and x2 as your input. So this model only has two possible inputs or two features. And each feature gets a weight or a parameter associated with it, which is the beta 1 and beta 2. And mostly linear regression type models will have an intercept, which is beta 0. And that's basically gives you the prediction for linear models type of things. And the loss function itself, it's going to be just the simple difference between your predictions and the actual values that you have squared. So if we say you are predicting age, it would be the predicted age for your model and the actual age of the person. And the difference between that would be your error or loss function. And on the right, basically you're seeing the flat surface, which is the red plane. That's the model's predictions. And the actual red dots are the true data. And the lines that you're seeing which are basically the difference between the predictions and the flat surface that you have. And the goal of the model is to find this flat surface in two-dimensional. This would be a line as good as possible. That's why it minimizes this error between the predictions and the actual values. And so if you plot the error or mean square error in the figure below, you can see the mean square error basically changes based on different parameter values of beta 1 and beta 2. And basically, there will be an optimal point where you pick those beta 1 and beta 2 values. That mean square error will be minimum, and that would be your ideal model that you want to find. And the procedure to find this optimal beta 1 and beta 2 is usually a gradient descent method. And we won't go more into details, but I'm going to stop here for a second and let Jerome basically talk about a couple of things which confused me. And when I was learning these things, it's what makes a model linear and what do we mean by gradients? So, yeah.
So in this example, what makes we say the model is linear because the prediction y is a constant plus a linear function of x. So each coordinate of x multiplied by constant beta 1, beta 2.
Right. So even if I had, say, x1 square or x2 square, this would still be a linear model. Because the model is linear in a parameter space, I guess. Is that what they mean by linear?
I would say it's linear. It's a linear function of the inputs of x.
Right. So what would make it non-linear? I guess that would be a better question to ask.
If when we plot y against x, the function was not a line.
Right. So if I had x1 times x2, would be a good example of nonlinear relationship?
I would say so, yes.
Cool. And do you have some intuitive explanation for what the gradients, what are gradients, or what is what do they kind of, if I had to think of them in terms of how to update my weights in the right direction?
So in the image that you show us at the bottom of the slide, the gradient would be the direction of the steepest descent. So if I placed a ball somewhere on this surface and dropped it, it would start going on in the direction of the gradient.
Right. Yeah. So it's mathematically it's a in a way partial derivative, I guess, in the, and it helps you find the direction where your loss function is getting smaller and smaller. So the question I was always get asked is it always unique, or is it always, do you always find optimal weights? And so that question again depends on the loss function. So for example, the loss function you have here, it's basically a parabola. And you can see as the, if you start at the one corner of this parabola, as the gradient descent works, you can find better and better weights, and the line that you fit gets closer and closer to the true values. So again, just to clarify, this is an example for just one input variable. So it's just a one single line and not a flat surface. And this is basically what happens with the gradient descent when you have simple linear regression models, where you do actually have one optimal point, and you will always find the optimal solution to your weights or model parameters. But that's not always true. So there are other complex models which may have much complicated loss functions. And in those cases, the loss function surface will be much more complicated, and you may have multiple local minimum possibilities, and there will be one global minimum, but it's likely that your algorithm gradient descent may get stuck into this local minimum as well. So sometimes, especially models like neural networks, which have highly complex loss functions and the surfaces, and it gets very difficult to find global minimum, and usually you usually have to stay happy with somewhat good local minimum. Is there anything else that I've missed for this part?
I don't think so.
Cool. Yeah, so that's what model fitting essentially means. Just to summarize, model fitting is essentially finding the model parameters that will provide you an output or prediction that is as close to your actual predictions as possible. Okay, so next topic is model regularization. So model regularization can be a bit tricky, but the basic idea of model regularization is, okay, so when you're trying to build models, we want to build models which are plausible and make common sense. And so we usually have some prior beliefs or understanding of the data we are working with. So we kind of know what the model should look like. So that's where the regularization comes into play. So for instance, if I know some certain disease or a certain symptom can be predicted with only a handful of genes, then I'm building a model which taking information from thousands of genes. I don't want to build a model that basically takes all those genes, but I want to get a model that will basically sparsify or reduce the number of genes that I'm going to be using for prediction. And that's kind of one way of embedding your belief in what the model should look like in selecting the model or defining the model that will give you good predictions. And the practical reasons, which are kind of linked to this whole prior belief thing, is basically if you have regularization, you can also help prevent overfitting. Like I said before, in many cases, the number of features we have are much larger than number of samples, which results in overfitting. We'll talk about this in a second as well. So any type of regularization is essentially minimizing the search space for all possible models you can have into a smaller search space. which is more likely to be plausible. And when something is more plausible to work, it will be more generalizable and less likely to overfit to your data itself. And there are two basically ways you can do this. It's basically, you can modify a loss function, or you can constrain your learning process. And I'm not going to go too much detail on all of this technicalities. What I really want you guys to know is there are two commonly used regularizations, especially for linear regression. These are called L1 or lasso, which what it does is basically adds another penalty term into your loss function. So if you look at the first red part, it's the same thing as I showed you before in the slide for the gradient descent. So on top of this, I'm just adding another term in my mean square error that basically penalizes based on my model weights or parameters absolute value. So, and what it ends up doing is basically makes only handful of model parameters to be non-zero, which basically sparsifies my model, and it basically picks handful of features that are more predictive of my outcome. So that's L1, that makes things sparse. And so the second one is called L2 or rich, and it constrains parameters to be small. And the way it does it, again, it adds another penalty term, but instead of just adding the absolute value of your model parameters, you're now squaring the parameter values and adding them as a penalty term. And this type of penalty usually makes the parameters to be small. And their small parameters are usually preferred over large parameters, and they tend to make models more generalizable. Yeah, anything else to add for this tricky topic?
Maybe to help get an intuition why it's a good idea to sort of constrain these parameters to be small. If we think of a situation where two of the features in X are very correlated, I could make essentially the same prediction by putting a big weight on one coefficient and a negative weight, equally big negative weight on the other coefficient. Right, so I might have like this several combinations of these two coefficients that sort of cancel out and eventually lead to the same prediction. So by preventing them from getting too big in either direction and shrinking them towards zero, I can sort of forbid or limit these kinds of large fluctuations.
Right, I think it's small, but it's also kind of discourage the impact of the noise in certain, if it is a large weight on a certain variable and it gets noisy, then your noise also gets amplified quite a bit. So I think that's a similar thing that you're talking about.
Yeah, and you also have some nice illustrations of overfitting a bit later on.
Right. So yeah, so don't worry too much about the equations, but the idea is to basically constrain the model in something that is plausible and will be more generalizable in real life. Okay, so talking about generalizability, this is a key point for model evaluation. And the way we do model evaluation, there are basically a bunch of things we have to think about. Because in practice, it's really easy to fit or train a model with scikit-learn or some other R package. The difficult part is to evaluate model correctly. And the standard practice to do this is basically you have data set and which you divide into train set and a test set. We'll talk about how to divide this in a bit later, but basically you have train set that we do the model fitting on, when that gives you a trained model. And then you use the test set on this trained model to evaluate the performance. So the key point here is your trained performance is not equal to test performance. So if you don't get too happy if you see your trained performance really, really well, 95, 98% accuracy, for example, it doesn't mean anything until that performance generalizes to test performance. So yeah, so that's kind of a key point. We have to separate train and test sets. So how do we do that? It's a good question, and we'll talk about this in the next slide. And there's another question that follows: how do we separate train and test set? How do we select which is the best model? So if you have multiple choices in developing model or training the model, how do we pick the best one? So we'll go over each of these one by one. Right, so the first point, like I said, the trained performance is not test performance. So on the figure on the right, you can see the orange line is the trained set performance and the purple line is the test set performance. And in the beginning, as your model is small enough, basically you're trying to you basically have similar train and test performance, but then it starts diverging at some point. And then once you pass this dotted vertical line, your test performance diverges from your train's performance. And that's essentially what's called overfitting. So this disparity between train and test performance on the right side is overfitting. Whereas on the left side, when your model performance it's close to train set, but not not the same as the train set, it could be possible that your model is actually not complex enough or doesn't have a capacity to represent things well enough. And then your test set will also suffer. And we can see this in a couple of examples. The first example is basically the regression example, where you have an input X variable and you're trying to predict output. And I'm fitting a line based on my training set. And I can do this in multiple ways. This can be just a flat line. I could have like a second degree polynomial, which is like a slightly curved line here. And I could actually make sure I have so many, I have a complicated curve that goes through every single training point. So which one of these is better? And we can only know that after we evaluate our performance on the test set. So now here you can see. So left side is what we call underfitting. Whereas the middle, the one in the center, you can see the purple dots, which are the test sets, have much closely aligned with the predictions. Whereas on the right side, you can see that even though the train performance was perfect on your training set, it's getting worse and worse on your test set. And so this is an example of bias and variance trade-off. And you can see that also in the classification example. So again, here your goal is to find a boundary between the two classes. You have X1 and X2. So the goal is to separate the circles from the crosses. And I can pick a simple model, which only has a linear line, or I can pick a second degree polynomial or a parabola. And that will be a more curved but smooth function. And the third one would be more complicated curve that will basically separate every single example in the training set in the orange class. And again, if you look at the test set, the one on the left or one on the right may not be the best case scenario, where we have either picked too simple of a model or too complicated of a model to differentiate between these two classes. And the optimal class is usually between, optimal model is between somewhere in the middle here. And the whole goal of machine learning is to find this optimal complexity of your model that will separate classes or predict classes in a generalizable way. So I'm going to take a pause here and ask Jerome if he has any comments about this whole bias variance trade-off. Like, so which one is the bias and which one is the variance trade-off, and which one you should be more careful about?
As you say, it's a trade-off between the two. So, for example, if I force my model to make always the same prediction, to have all its coefficients set to 0, there's no variance at all in its predictions or in its parameters, but it's a very bad model because it has a lot of bias. And on the right of your slide, if I let the model do whatever it wants, it will fit perfectly the training set. So it's not biased, but the model coefficients and the predictions have a lot of variance. So if I resample a slightly different data set, if my participants were slightly different, I would find a very different decision boundary. And that also results in bad predictions. So as you show on the figure on the top, we have to sort of find a trade-off between these two sources of error.
Great. Yeah, the interesting thing for me is, I realized this bit later. So here the bias is really bad because this bias is in the predictions. Whereas when you're doing regularization before, we are also introducing bias to the models, right? So, but this is a good bias. We are trying to bias the model into something more plausible. Whereas here, the bias is a bad bias because it's biasing the predictions themselves. And that was something, again, something that confuses people when the terms are overloaded. But yeah, was it something confused you as well, or?
Even if it's not necessarily the decision to shrink the coefficient is not necessarily based on some prior knowledge, or if we don't have a strong reason to think small weights are more plausible, the fact that we add this penalty, it biases the coefficient, yes, but it reduces their variance. So, but bias is always bad, it's an error, but by paying this small price in bias, we're able to reduce a lot the variance of the coefficients and reduce the total error, which is what we're interested in.
Right. Yeah, I think that's a better way to think about this. I think we are actually playing with the trade-off to reduce the error by introducing some bias. We are reducing the variance. Cool.
And maybe if I can ask a question. Mm-hmm. Here, the model grows more and more complex. So it goes from a linear decision boundary to a very convoluted one. But when you talked about the ridge and lasso regularizations before, in all cases, the decision boundary is linear, right? Yes. Or in the case of regression, the output is a linear function of the input.
Like this one, yeah.
So how does that map to what we are seeing here? How does shrinking the weights make the model simpler?
So for lasso, I mean, here we only have one variable, right? So if we had more variables, this would be a 3D plot, and you would be fitting a surface instead of a line. By saying this is the predictor or the feature is only one, we're already shrinking the search space for the model to one dimension. So that by inherently creates more simpler models than if you had two variables as your features. But on top of that, each variable can also be model. The model can have just take the first order polynomial or second order polynomial or a much higher order polynomial. So that's a different level of complexity you're adding to the predictions. So yeah, that's how I see these regularization versus what we're trying to fit here is a hyperparameter for the polynomial degree. Does that make sense?
Yeah, I see. Okay, so we were reducing the set of values that the parameters can take.
Right. Yeah. Whereas rather than just reducing the number of parameters themselves through sparsity in the prior example. Cool. So moving on to cross-validation. So this goes back to the second question in the model validation is how do we even sample, train, and test set? So, so like I said before, the train set is meant to just learn model parameters or the function that maps from X to Y. And the test set is meant for evaluating the model performance. So you never use anything from the test set during your model training. But again, why only pick one train set and why one test set? I could have picked a different sample for my train set as well. And that's essentially what cross-validation does. It will resample different train and test sets. So the figure on the right basically shows, say, if you have a data set, say, of 100 subjects, you can divide them into 5 pools of 20 subjects each. And in the first round, you will take the first 80 subjects to your train set and the last 20 subjects to your test set. And then you're just basically shifting the test set to different folds. So you get different samples of your train and test set. And then at the end, you can average all your performance metrics on these 5 different folds of test set. And this is essentially considered as an outer loop for cross-validation. You're here basically just shifting train and test splits and measuring the performance on the test plate. And there are different ways to do this. Again, I won't go into detail, but if you look at in the scikit-learn, you can see k-fold and shuffle split, which are more commonly used cross-validation procedures. And yeah, anything else to add here?
No, again, as you said, the key point is that we use the orange data, the training data, to estimate the model parameters, and then we check how well they do on different data. Right. Because if we pick the best model parameters that give the best solution on the orange data, then almost by construction, they will perform well on this orange data. But as you explained, they can overfit the noise in this training data and perform poorly when we receive some new unseen data, which is what we're really interested in, to make useful predictions on new data once we have fitted and distributed our model.
Right, exactly. And just to, one note is that when you're doing this, we're using the same model for all of these train and test splits. You're not changing the model that you have that you're using here. But what if I want to try multiple models? So this is where the so-called inner loop comes into play. So what happens is each model comes with its own set of hyperparameters. We'll talk about this in the next slide a bit, but these are essentially parameters that decide the architecture of the model. And you can also pick different types of model architectures. Like I mentioned before, you can have SVMs, random forest, linear regressions, neural nets, all of that. And there are also different things you can try to transform your features. And we will talk about this in our second module. But so basically the idea is there are different choices you have to make when you're actually picking a model. And so to do that, we need to further split our train data into another loop of cross-validation. So again, so if you have 100 subjects total in your all data, you're picking 80 to be in your train set. And then this train set can be further divided into 4 subfolds of say 20 each. And out of those four folds, the last fold you treat it as a validation data. And then you basically try out all the variations of your model on this train set, and then evaluate them on your validation data to basically select the model that you think will work best on your test data. But here you do not touch your test data, because that would be then peeking into what the test data looks like, which is never an option in real life. You never have access to test data. So this is kind of a validation trick that you basically use your train data to do your model selection. And then once you select the model, then you basically evaluate it on the test data. And just like the previous slide, even this, you can do it multiple times by shifting the validation sample to different folds. And every single time you're basically picking a different subsample of your data to evaluate different model hyperparameters and architectures, and see which one works best on this inner loop before you test it on the test set. Anything else to add here?
Nothing to add, just that this is so important that we'll talk again about it in the next session as well.
Yeah, it's extremely important. Just one little terminology note here. Some people call the test data to be validation data and validation data to be test data. It doesn't really matter what you call, as long as you're consistent. So don't be confused if people change them, use them interchangeably. The key point is that you do not look into the held out data set during your model training or model selection. Cool. So yeah, like I said, what are hyperparameters? The key point of our hyperparameters is that they are something that you choose. They're very difficult to learn. So model parameters or the weights are learned through the data, whereas hyperparameters is something we pick. And the examples would be the degree of the model for the regression models, the ones I showed you for the overfitting examples. There'll be kernels for support vector machines, number of trees for any ensemble method like random forest. And for neural networks or deep nets, there are just a multitude of factors that you can, or multitude of knobs you can basically tune to train the model. And this includes number of layers, filters, batch size, learning rate, and many, many, many more. And also, we talked about regularization a bit, and you can also control the amount of regularization. There's an example for ElasticNet, which controls the amount of L1 versus L2 regularization that you want to add in your model. So all of these parameters, or I should say hyperparameters, need to be picked. And the way we pick them is through the inner cross-validation loop that I just showed earlier. Yeah, so the key point about this can really blow up in their numbers. So sometimes you just pick them arbitrarily, and sometimes you also do a computationally feasible grid search. But again, it really depends on how many hyperparameters that you want to go through. And they can really grow really fast, especially for neural networks. I think, yeah, I had a little question here when I was learning about this, and I always wondered, why can't we just learn the hyperparameters? Do you have a good, like, some insight on that?
I think if you look at the regularization hyperparameter, for example, for the linear regression with the ridge penalty, when we say learn in machine learning, we mean fit some parameter to the training data. So find the value of our parameter that yields the best prediction on the training data. Since the goal of the regularization is to bias the parameters away from a perfect prediction, which happens when the model is overfitting, if we try to learn the hyperparameter that gives the best prediction on the training data, then the best hyperparameter we find will always be no regularization at all, because we are trying to prevent the model from fitting too well the training data with this hyperparameter. So the hyperparameter defines a family of functions in which we look for the association between x and y. And then within that family of functions, we learn the parameters that yield the best prediction.
Yeah, no, that's exactly right. And there are some other ways you can do for, especially for neural nets, so where you can try out different parameters and update your hyperparameter based on your actual prediction scores. But that gets very computationally expensive. So that's also a problem in practical sense. Even if you could learn some of these parameters through a lot of computational search, it gets very computationally difficult to do that. Right, I think we're almost there. So the last topics we're going to talk about is, okay, how do we even look at the performance? So I think this is something that really depends on the problem you're trying to solve. And it's definitely different for classification and the regression models. Here we're going to mostly focus on binary classification, because there are a couple of key ideas that are easily confused by the people when you're learning for the first time. So these ideas are essentially what type of errors do we get in classification problems? So there are two types of errors. Some of you are familiar with statistical analysis before, so you must have seen the type 1 and type 2 errors. So in machine learning jargon, they essentially translate to false positives and false negatives. And you can see that from this figure on the image on the right. So what is going to be a false positive and false negative error in practice. And you can show that in your results in a form of confusion matrix. So what confusion matrix basically shows is basically like it's a 2x2 rubric for binary classification, where on the columns represent the ground truth, and the predictions represent the rows. And basically, if you're correct for predicting the right positive outcome, in this case, if you're pregnant or not pregnant, it would be the true positives. And if you have a type 1 error, that would be, or the false positives would be here, because your ground truth is negative and you're falsely predicting it to be a positive, and vice versa. There's a false negative here for your predictions and true negatives here. And this should become more clear with this example here. So for we are building a model, for example, that will detect COVID from the chest CTs. And the current COVID prevalence in Canada, I think I checked it yesterday, was 1 in 1,000. So the false positive would be that model predicts that somebody has COVID when the person actually doesn't have COVID. So based on CT X-rays, it's a false positive. And the false negative would be the converse, would be it's a person is healthy, a person is predicted as a healthy person when the person actually has COVID. So the key concept here is, okay, so since our prevalence is so small, as in the number of COVID people in the population is very few, we could just do a dumb model that basically predicts everybody as healthy. So what does that mean? So it basically means if I'm predicting everybody as healthy, I will have 0 false positives. So nobody will actually get ever predicted as COVID. So, but this causes a problem. And the problem is basically that if my model only predicts everybody as healthy, my accuracy is still very, very high. So since I'm only going to make one mistake in 1,000 people, right? So my accuracy is going to be still 99.9% or 0.999. And this might give us a false sense of happiness or that our model works great. But whereas our model is just a dumb model that predicts everybody as healthy. So in scenarios like this, it's very important to look at a few other metrics or measurements of your performance. And namely, one of them is a precision. So precision would translate as follows for this particular case, that how many of those who we predicted as COVID to actually have COVID. And that basically is a ratio of the true positives over true positives, or all the positives that we have. And for this particular model, this will not even be possible to calculate because we are not having any positive or COVID patients at all, or COVID predictions at all. So by having this matrix, the other one is being recall, also known as sensitivity. We can see that our model actually is a stupid model that only predicting one class the whole time, and it's not really useful. So it's really important that we look at different metrics other than accuracy to understand if our model is actually predicting something useful, or is just predicting something that may give a sense of high accuracy, but it's not really useful in the real practice. And I'm not going to go into all the details of here. You can definitely look them up online or just read this again. But the key point here, especially when you have uneven class distribution, by what I mean is you have very small number of positive or negative cases in your entire sample. You need to look at other measures of performance, such as precision and recall. And you might also have seen ROC curves, which do something similar. Try to trade off basically the true positives and false positives here. Again, in like some cases, you want true positives are okay, whereas false positive are false positives are okay, but false negatives are not okay. Again, in COVID, it's okay to have false positives because you can still quarantine them and that'll be okay. But if you have false negatives, then we are basically sending people back into population which have COVID, and that's a really, really bad thing. So depending on what type of models you want to build, you want to trade off either false positives or false negatives. And these curves basically help you decide how to make that trade-off. Yeah, the last couple of slides are basically slides for like just to think about the recent advances in machine learning. And one of them, again, the deep learning is a very popular one. And the reason it's very popular because it really truly works really amazing on structured input. So here is an example of structured input and image. And basically what I mean by structured is basically you are mixing the pixels, nearby pixels have a intrinsic relationship or the structure within them in images. So they are not completely independent from each other. And they work really well with the images and the speech and the language models. But at the same time, they have large number of parameters, so they need a lot of data, and they have a large number of hyperparameters, which need a lot of computational resources as well. So they get difficult to train. So particularly for life sciences, like I said before, I've been using them mostly for medical image analysis. So if you're looking to segment some medical images, this would be a really good model to work with. And yeah, but like I said, they require a lot of data, which is hard to come by in medical field. So yeah, anything else you want to add, Jerome, for this type of models?
Yeah, I was wondering, why is it called the deep learning?
Oh yeah, so the deep learning comes from the fact that, okay, there are multiple layers. So each layer is essentially learning more features based on the previous features. And this architecture is kind of inspired by the visual cortex in brain, which also has multiple layers. So as the notion goes, like as you go higher and higher in your layers, you are learning more deeper and deeper understanding of your data, which gets, so you're, the first layer, for example, you will just learn simple features like edges between the pixels. In the second layer, you might learn some shapes. And in the third layer, you might learn some more complicated shapes that resemble the number 2 or number 3 or number 4. So this hierarchy of features is what makes the models deep, as they say. Cool. I think we're going to finish with the last couple of slides of things not to do or things which can be problematic. Again, so we talked about generalization and importance of cross-validation, but it's also possible that your models will not generalize from one data set to another data set, because again, that if your train and test sets are within the same data set, you're still using the information within that data set. So in the real practical examples, it gets very difficult. It's not easy to build a model that will generalize over different data sets, especially if each data set has some implicit biases. For example, you have North American demographics, which may not translate to Africa or Asia type of demographics. In medical images, it's another problem is the noisy labels. People don't really agree on, for example, on the diagnostic labels. So what makes somebody bipolar or autistic? It's these are questions they're debated still. So we may have labels which may not be agreed by different people. So how do we train models on those type of labels? And something I think what Jerome is expert on is understanding the data distribution shifts, where you have some type of data distribution in your current data set, and that can shift either over time or with location. And then your model needs to understand how to adjust to that shift. And I'll let Jerome explain that a bit more.
Maybe just to give a concrete example, if I have learned to predict some disease from a medical image, sometimes I get very good score with quad validation, even if I separate correctly from a data set, the training data and the test data. And then when I try to deploy this model on data from a different hospital, for example, where the images were acquired with a different scanner, it doesn't work at all anymore. So because the distribution of the images and the association between features in the image and the disease is different in this new scanner. That would be an example of data set shift.
Right. And so these are kind of like, unavoidable problems, because you're going to get upgrades for all the hardware you use every few years. And one thing also you should all definitely ask, if I really need like a giant deep net because it's popular, or can I make do with the simpler model? And often the case, especially in the life sciences, like we can definitely make do with smaller models before we get into larger models, especially given how amount of data we have. So yeah, I'm just going to conclude with these slides. If you want to remember one thing from this presentation, is that supervised models are useful for predictions. We are not really trying to explain the phenomenon directly. We're just trying to make accurate predictions. They're really good for image segmentation, prognosis, drug development, and similar problems. And our job as a machine learning expert or a machine learning user is to ensure that these models are generalizable. And the only way to do that is to do very different, many types of validations. The cross-validation is just one way and the most basic way of doing that on your data set. But you really need to do that, repeat that thing again on multitude of data sets to make your model generalizable. And it's not always possible to do that with all models. But in that case, you still want to understand if your model is biasing, has certain biases. It could be just male-female biases in predictions or some sort of other demographic biases. But it's important to make some post-hoc analysis to understand these biases. And lastly, I'm just going to leave you guys with a thought. It's in that I have realized over the years working with machine learning is like we are essentially doing this as engineers. So we are building tools as if we are building bridges in civil engineering. It's rarely used directly for scientific discovery. It's just a tool that will help us make predictions. So the interpretation of what machine learning model is doing, it's extremely complicated. And but there's definitely research going on these days that basically build model which will explain where the predictions are coming from. But it's still in a nascent stage. So until then, the interpretation and explanation of what machine learning models is doing is essentially a black box. So do not read too much into it. All we are doing here is just building a tool that will make accurate predictions. And I'll let Jerome have some final thoughts on these topics, and that should end the presentation.
Yeah, I agree with you. That's a very important point, that the fact that the features we use predict well the outcome or the output we're interested in doesn't tell us much or anything about the nature of the relationship between these two things. So maybe, for example, the disease causes the features we see in the image. Most likely it's not the other way around. Maybe something else influences both and causes this association. All we know is that using the image, we can predict whether the person is has the disease or not, but it doesn't tell us much about the mechanism that links these two things.
Yeah, no, exactly. I mean, sometimes it's important, sometimes it's not. For example, if I'm just segmenting the image, it's okay for me to not know how exactly it's doing, as long as it's segmenting the image or labeling all the brain regions or other organs correctly. So I don't want to. I want to highlight that these are extremely useful models, but we have to be careful in terms of what their purpose is and what kind of things we can take away from these models. And yeah, with that, I think we're going to end the part one. And I'm going to thank Jerome for helping me present this material. And I will move on to the second part with Jerome explaining mostly about unsupervised learning models in machine learning. And that's it. Thank you very much.
Thank you.